Hi there. In this video, we'll look at problem 10 from the semester exam review packet. Here we're asked to write the linearization of this function at this particular x value. So to find the linearization, we're going to want to compute the output when x is 1 and the derivative when x is 1. And we'll organize those into a linear equation. So let's get started. Okay, when we replace x with 1, we get 3 times 1 squared, which is 3, plus 1, which is 4. So f of 1 is the logarithm of 4. Okay, next let's calculate the derivative and then plug in 1 for x. So recall that the rule for the natural logarithm function, if we have log u, then its derivative is 1 divided by u. So we'll write 1 divided by this expression here. And of course the chain rule applies, so we'll multiply by the derivative of that highlighted expression, which is 6x. Okay, next we just need to plug in 1 for x. So when we replace x with 1, we get this expression here, which gives a fourth times 6, or 6/4, which is 3/2. Okay, so now we've collected the information that we need to write the linearization of f of x when x is 1. I'll write Lx for the linearization of f. Alright, so if we rearrange the slope formula, we get the output, which is log 4, plus the slope, which we found to be 3/2, times x minus the input, which is 1. And this formula represents the linearization of f at x equals 1. Part B. Now we'd like to use that linearization to find an approximation to the function. Okay, so let me go ahead and paste this over to my next screen. Okay, and we can use this linear formula to approximate values that are close to 1. And we're just going to plug in 1.2 as an input. Okay, so let's see what goes on here. We're going to subtract 1 from 1.2, and that gives 2/10. And let's see. Half of 2/10 is 1/10, and we want 3 times that. So that should be 3/10. Alright, so our approximation is the log of 4 plus 3/10. We could use a calculator to get a decimal value for this expression, but that's good enough for me. Is the approximation too large or too small? Well, let's stop and think about what that is saying. If the appearance of the graph is like that, then a tangent line will produce an answer that's higher than the actual graph, and we'll say that the output is too large. The approximation is too large. If, on the other hand, the graph looks like that, then its tangent line would lie below the graph, in which case we would expect the linearization to be smaller than the actual output. Okay, and what is it about these curves that makes them different? Well, this curve is concave down, and this curve is concave up. So by analyzing the concavity of the curve, we can determine whether the linearization is too big or too small. So for that purpose, let's calculate the second derivative of this curve. And if you don't mind, I'm just going to utilize my previous work in which I calculated the first derivative. Okay, so let's go to work on this expression. Okay, it wouldn't hurt to simplify this a bit. So let me just combine it so that it looks like one fraction. And now we have a choice to make. Do we want to apply the quotient rule or simply use the product rule? I suppose it won't hurt to use the quotient rule here. So we'll take the denominator and multiply by the derivative of the numerator. Minus the numerator times the derivative of the denominator, divided by the denominator squared. Okay. And let's see what we can learn from this expression. Let me do a little bit of simplifying here. When we multiply through by 6, we get 18x squared plus 6 minus 36x squared and if we combine terms in the numerator, we get 6 minus 18x squared divided by 3x squared plus 1 squared. Okay, and the point which is of interest to us is the point where x equals 1. So let me go ahead and throw 1 into this formula. Oops. And let's see what we get. So f double prime, evaluated when x is 1, is going to be 6 minus 18 times 1 squared divided by 3 times 1 squared plus 1 squared. And we do get a value which is negative. If the second derivative is negative, then the original function must be concave down. And so we expect that that tangent line is producing an approximation which is going to be larger than the actual value. Thus, the approximation is too large. Okay, let's pop over to Desmos and see if everything's looking reasonable. So here I've just used the Desmos tool to graph the original function. And let me see if I can just write on this screen. Okay, when x is 1, we get a tangent line that looks something like that. And indeed, for 1.2, you can see that the tangent line lies above the graph, and so yes, it should be too big in that area. Okay, I hope you found this video helpful, and we'll see you next time.